Chapter 4.3 is about the product and the quotient rule. These are two new rules that we can add to our toolbox of differentiation rules. So far what we learned in the previous section was the scalar multiple rule, the constant rule, the power rule, and the sum and difference rule. So now we're going to be able to use these two rules as well as we come across them in various functions. The other thing that we're going to look at is what we call higher order derivatives. So let's look at what we were able to do before. So if we ever came across a function like this, you have two things being multiplied, you would not be able to derive the first factor and then multiply it by the derivative of the second factor. And first of all, we never had that rule and it just doesn't exist. So we were forced to rewrite. So here I would distribute that x to everything, and there is my rewrite. Now what I could go ahead and do is when I try to derive this function, I would be able to apply the derivative piece by piece. That's the sum and difference rule. There's my sum and difference rule. And then I would be able to use my power rule. So I would pull down my exponent as a factor and then reduce it by 1, whatever it was. So it's going to be 1 minus, this had a power of 1x to the, and then I would reduce my exponent by 1, so it would be 0. So when you simplify, it's just 2x minus 1. Same thing for down here. I am going to have to rewrite, and I would get x to the 1/2. You would have to go ahead and distribute that in as well. So know if you take x squared times x to the 1/2, this is one of those properties that you have two powers of the same base, in this case x. And what you can do there is add those exponents, so 2 plus 1/2, which when you multiply top and bottom by 2, you're going to just get x to the 5/2. So this would be rewritten as x to the 5/2 plus x to the 1/2. Then you would use the same type of rules. Note, I have not derived anything. All I did was rewrite, and now if you wanted to, you could use the sum rule and then also the power rules. This one actually was one of your homework problems, so I'm also going to rewrite this because, again, we did not have that ability to say let's derive the top and then derive the bottom and divide the two. You would again have to rewrite x to the -2. You would take that factor across the line, change the sign, and it is a factor, so you would multiply that by everything, and in the end your rewrite would be. So again, haven't derived anything, but you could at this point by just using, it looks like you have a scalar rule there, you have some power rules, and then you have the sum and difference rules. Okay, so I want you to just take a moment to absorb this. If you were to try to find the derivative of x by finding the derivative of that first thing being multiplied times the derivative of that second thing being multiplied, you would not get the correct answer. This is not how we derive products. So I just want to show that if you derive x, you're going to get 1x to the 0, which is just 1, times, if you derive this piece by piece, you're going to get 1 minus 0, and that's just going to be 1. So you can see this is not the right answer compared to what the derivative should have been for this function. So this introduces the product rule. The product rule states that if you have two functions or just two expressions being multiplied to each other, what you can do is derive it using this rule that you would leave the first factor alone, multiply it by the derivative of the second, so you would actually derive that second piece of it and multiply them together, and then you would sum up, now leave the second one alone, and derive the first piece or the first factor. So we will do an example of this, and it's going to be that same one that we just encountered in the previous slide. If you had this, you have these two, what in this notation, what this would have been called is your f of x. This would have been your g of x. Okay, it's two things, two functions or two expressions that are being multiplied. If I were to derive, here's what I would do. I would leave my function, my first one alone, but then I would derive my second. So I'm just going to write this out first. I'm not going to derive anything. I'm just going to show you what I have to do. I'm going to leave my second one alone, but then I'm going to have to derive my first. Alright, so I'm still not going to derive. What I would have to do to derive this piece, after using the product rule, I also have the sum and difference rule that I would use here. We are deriving in terms of x because that's our independent variable. So the derivative of x minus the derivative of 1 plus x minus 1 left alone, and then times the derivative of x. Again, no differentiation has actually occurred. I'm just showing you where the differentiation has to happen. So now x times, and then the derivative of x, there's my power rule, that's just going to become 1, minus the derivative of a constant is just going to be 0. We have x minus 1, and then the derivative of my x to the first is just going to be 1 again. When you simplify this, it's going to be x times 1 plus x minus 1. Technically, you don't need the parentheses there, so you just get, and take those out, 2x minus 1, which is exactly what we said it should have been in the previous slide when we rewrote. Your book is going to have answers, and they're going to be simplified, or what they state as simplified. And what they often do is, if there's any shared factors in the terms, you're going to pull out that shared factor, and you're going to pull out whatever one has the smallest, oh, this should say common, common power. Okay, and I'll show you what that is in the second one. Just make note of this, that's how your book is going to be simplifying your answers. What they ask you to do is do the product rule. So I am going to a point, rewrite this. I'm going to take the derivative, and we are having a variable of s, so we are going to be deriving with respect to s. And I am going to rewrite this as s to the 1/2 times 4 minus s squared. Okay, so here is what I'm looking at deriving. So in order to do that, we need the product rule. So the product rule once again states that if you have two expressions or two factors, you can leave the first factor alone, s to the 1/2, times, and then the derivative of the second. But then you sum up, now you leave the second one alone, 4 minus s squared, and you derive that first term. Okay. So again, no differentiation has actually occurred. I'm just showing where the differentiation has to happen. So here I am going to use the difference rule, that we can derive this piece by piece. Okay, and then plus this one left alone, 4 minus s squared, and this is d ds s to the 1/2. Now that I know where all the differentiation has to occur, I've used all my rules as they came along, so I'm going to actually apply the differentiation. So here, the derivative of 4 is going to be our constant rule, so it's just going to be 0, minus, and then here's a power rule, 2s to the first, but I'm not going to write that because we don't do that. And then we have 4 minus s squared, and then here we're going to bring down that 1/2, and then it's going to be s to the negative 1/2. Alright, so now I'm going to simplify this. I'm going to just get, ooh, that should be minus, sorry. So minus, yeah. So we're going to have minus 2s, and then we have s times s to the 1/2. So add those exponents, we're going to get 3/2. Plus, and then we have 4 minus s squared, and then this factor right here. So I am going to simplify this a little, oh no. I'm going to leave that. I am going to take this as a separate factor though. So what I want you to see is we have these two chunks. We have this chunk and we have this chunk. So I think the biggest thing is that you're going to need to do is be able to tell if your answer is correct. And so when you look in the back of the book, will you be able to match what they have in the back of the book? So what they often do, they'll pull out the power with the smallest exponent. So here is our smallest exponent. And if you have any types of fractions, they're also going to pull that out. So what I'm going to say is I'm going to divide everything that I have here by 1/2 s to the negative 1/2. And then so divide this by 1/2 s to the negative 1/2. So keep in mind what that's doing is this is going to cancel out. These are going to cancel out. Okay, and then also over here you have negative 2 divided by 1/2. That's just going to be negative 4, and you're dividing common base powers. So if you do that, you actually subtract the exponents. So 3/2 minus negative 1/2. So that's just going to be turning into a positive. And what you are going to get when you do that is 4/2. This one is going to become, like we said, we simplified this piece of it, times, and we're going to simplify this to be s squared. And then plus, we have up here 4 minus s squared. And then now we divided everything by 1/2 s squared, so you also have to multiply everything by 1/2 s to the negative 1/2. So I think I said that wrong, but what we did was we divided the whole thing by 1/2 s to the negative 1/2, so we have to multiply everything by 1/2 s to the 1/2. So now you can simplify what's going on in here. These two are like terms, so what you're going to get is 1/2, and now this is where I'm going to cross the line, change the sign, s to the 1/2, and then all up on top times, this is negative 5s squared plus 4. So your final answer and what they will have is this in the back. Ta-da! Yeah. So algebra, once again, biggest thing is if you have an answer, play around with it because the back might have done something a little goofy. They might have condensed things. They might have pulled something out like they did here. They pulled out the 1/2 s to the negative 1/2. So you got to play around with these things. Cross the line, change the signs where you need to. It becomes a whole algebra game. The next thing that we have is what we call the quotient rule. And the quotient rule states this: low to high minus high to low all over low squared. That's basically what you want to remember in your mind when you think quotient rule. Low to high minus high to low all over low squared. And it's a little bit more easy to remember if you say it in a southern twang accent. So we will do one. I'm going to do number 15. Which states this. So low to high, we're going to find the derivative of this. So I am not going to derive anything. I'm just going to set things up. I want my low, d high, minus high, d low, all over low squared. So a little bit of a mess, but we can simplify these. So now keep in mind that I haven't derived anything. I'm just setting us up what we need to do. So we have x minus 3, and then the derivative of x squared minus the derivative of 4. Okay, that's that piece right there. Minus, and then x squared minus 4, and then the derivative of x minus the derivative of 3 all over, oops, low squared. Oh, sorry, that got messy. Okay, so now I'm going to actually apply these rules. We have x minus 3 and then 2x minus a constant. Okay, minus, we have x squared minus 4 times, and then 1, and that's it, all over x minus 3 squared. So slow this down, see where I got everything. This 1 came from 1 minus 0 because that was a constant rule. So now we're going to get x minus 3. I'm going to just cross this off. We can distribute that in. We're going to get 2x squared minus 6x, and then minus, be careful with your distribution. That 1 really doesn't do anything, so I'm just going to cross that out. Minus x squared plus 4 all over x minus 3 squared. And I can combine some like terms here. These ones will combine. We're going to get, sorry, I'm going to have to put it up here. We have x squared minus 6x plus 4 all over, and then x minus 3 squared. If you could simplify anything here, you would want to do that. I can see that I will not be able to FOIL that or factor that out, so I'm just going to leave it exactly as it is. So there is my derivative. So this one actually does ask you to find the derivative at a particular c, and they gave us the value c equals 1, so they said find f prime of c when c equals 1. So in that case you would actually just plug in your 1, so 1 squared f prime of 1 equals 1 squared minus 6 times 1 plus 4 all over 1 minus 3 squared, and we're going to get, so the derivative of this function at the x value or the c value 1, when you plug in 1, is going to be a slope of negative 1/4. The final thing that I want to just say is you can derive and continue deriving for as long as you want. If you wanted to derive this, you would take each one, so I'm going to just do this really fast here. I'm going to drop down my exponents as multipliers. We're going to get 15x to the second. We're going to get 1, and then this one drops out. I could derive this again, and what I'm going to do is I'm going to do the derivative derived. Okay, so I'm going to do the second derivative is what we call that. So I'm going to drop down my 3. We're going to get x to the second plus 30x, and then plus 0 because that drops out. I could derive this again if I wanted to. Right, so this would drop down. We get 24x to the first plus 30. This is when I could derive again. We actually start putting numbers up here. So this is the fourth derivative. All right, and I'm going to just only get 24. And then after that, I mean, we would only be at 0 the whole time. And dot dot dot. So the higher order derivatives is just deriving again. Here is one of the notations that we use for it. There are other ways. So if I wanted to derive with respect to x, I could call it dy dx. If I wanted the second derivative, what you do, it's like the second derivative, and you're going to be deriving x twice is what it would look like. All right, this one would be d to the third y. So derive the derivative, the third derivative, and so you're going to derive around x 3 times, and then and so on. One kind of interesting thing is regular old function, what we started out with, that's often associated with a function of displacement. It's just some sort of change happening over time. If you derive it, then you're finding the velocity. It's the instantaneous rate of change. If you derive the velocity, what's the rate of change of the rate of change, or what's the rate of change of velocity? Think about in your car. As you're speeding up, your rate of change or your rate of speed is changing. That's your acceleration. Third derivative is actually called jerk. It's the rate of change of your acceleration. Fourth derivative is called snap. Fifth derivative is called crackle. And then, yes, sixth derivative, that's right, pop. All right, so there's your assignment.